Hi all, today we will see an important topic which is known as pipeline processing. And the concept of pipeline processing comes from, I'll correlate it with a real world example so that you can understand better. Let us assume there is a company that manufactures chocolates. It is a chocolate manufacturing company. In that, there are different tasks. The chocolate manufacturing process has been divided into different tasks. One task is mixing of material. Second task is mix preparing material. Task 1, mix material, cut the chocolates into shapes, and packing. Let's assume these are the 4 different stages in the complete chocolate manufacturing process. So here the first stage, I supply some materials, so it provides all the materials and give it to mixing of material. After mixing of material, it will give to the processing unit, which cuts the chocolates into some pieces, and then packing of chocolates. So here the 4 stages, these are the 4 stages of the process. And very first time when I give the material, the T1 is prepares the material and handovers to the T2 process. When T2 is doing mixing of material, can you guess what T1 might be doing? Yes, T1 might be uh, preparing the material for next set of chocolates. So T1, T2 both are busy. Now the moment T2 completes its process, it handovers it to T3. When T3 is cutting the chocolates, cutting the pieces, the T2 is busy with mixing of the next material. Likewise, T1 is busy with preparing material. So by this way, what's happening? Both T1, all T1, T2, T3 are busy. They are not idle. It's not like T3 is not sitting idle until T2 is complete. T3 is doing some other task. The moment T3 completes its task, when T4 is doing packing, T3 will do this. Let me explain with a proper example so that you can understand better. It's really necessary and important to understand this pipeline processing. What is its exact significance? Let us assume I have material 1 and material 2. Let me draw the picture like this. Let's assume this is material 3 and this is material 2, and this is material 1. So when T1 is doing, first T1 will do the process material 1, handovers to T2 for mixing of material. When T2 is doing mixing of materials, what happens? T1 is doing mixing of material 2. Similarly, when T2 completes its task, and handovers to T3. So M1 is now here. Next M2 is here. Next M1 is here. So when M1, M3, when T1 is doing mixing of preparing the material 3, T2 is doing mixing for material 2, T3 is cutting material 1. Similarly, when it handovers to T4, now M1 is here packing. When M1 is here, M2 is here. When M2 is here, here is M3. And here you may get some new thing like M4 if you have. So this cycle goes on. Let me repeat it. It is very important to understand. So I have a chocolate manufacturing company and its task has been divided into T1, T2, T3 and T4. There are, this is M1, let's assume, and this is M2 and this is M3. So when M1 moves here, when moves here, M2 comes here. So when M1 moves here and here finally, in the 4-step process, because this is 4-step, 1, 1, this is 4 stages, 1, 2, 3, 4. So in the first stage, M1 is here. In the second stage, what's happening? When T2 is doing M1, T1 is busy with M2. So likewise, when, so let me repeat this. This is doing this one. Next, this is doing fun. When M3, when T3 is doing M1, T2 is doing M2 and T3 is doing M3. This is the process. Similarly, at T4, at 4th stage, when T1 is doing M4, T3 is doing M2 and T2 is doing M3 and maybe T1 is doing some new thing called M4. So from 4th cycle onwards, what happens? You get output. See, if T1 takes 5 seconds, T2 takes 5 and T4 takes time total 20 seconds. After 20 seconds, for every 4 seconds, for every 5 seconds, you get the output. This is called pipelining. I hope you are understanding this. It's a very important topic. So this pipelining can be achieved by using a single processor. So we know about parallel processing and sequential processing. Sequential processing, that means when you have uniprocessor And this parallel processing is when you have multiple processor. But the specialty of this pipeline processing is that even though you have uniprocessor or single processor, you can achieve parallelism, parallel processing, which is called pipeline. By dividing the task, this is called pipeline processing. And it's very important processing technique. uh, I hope you are getting what I'm trying to say. See, let me repeat that. Similarly, you can resemble with this is like instruction execution cycle, which contain four stages like fetch, decode, execute, and store. So instruction cycle has been divided like if I correlate instruction cycle, this thing, instruction execution cycle, what it contains: fetch and decode and execute and finally store. The fetch, decode, execute, and store. So these are my instructions. So can you guess when instruction 1 is getting stored? When instruction 1 is getting stored, what execution phase might be doing? It might be executing instruction 2. When it is executing instruction 2, instruction 3 might be in the decode state and the instruction 1 might be in the fetch state. So this is what happens in general. So this is the basic idea behind pipeline processing, and let us discuss in detail about this pipeline processing, what it is, and why it is used. And it's very important to have this technique. So let me uh, repeat the process once again, and it is very important to have an idea. So first we'll see the introduction. Pipeline processing is like a series of stages. As I said, pipeline processing consists a series of stages where some work is done at each stage in parallel. Like we have seen, pipelining is a series of fetch, decode, execute, store, where some work is done at each stage in parallel. And these stages are connected to one to the next to form a pipe. So this, for that reason, this has been given the name pipe, because the output of fetch is sent to decode and output of decode is sent to execute and output of execute is sent to store. So this is about fetch, decode, execute, and store. Similarly, when I have fetch, decode, and execute, store concepts, uh, the output of fetch, that is, the output of fetch acts as a input for decode. Similarly, the output of decode is sent as an input to execute. Similarly, the output of execution is sent as a input to store. So these are stages are connected. For that reason, we are referring it as a pipe. Pipe means these are the different stages and which are connected. For that reason, it is called pipe. The stages are connected to one to the next to form a pipe. Instructions enter at one end and progress through stages and exit at other end. That means in fetch, decode, execute and store stage. So the instructions are and they are connected and they are in a pipe. Now when you instructions I1, I2, I3 enter at the pipe, crosses each stage and the output is the result of this instruction. So the stages are connected to one to the next to form a pipe. Instructions enter at one end, progress through the stages and exit at other end. A pipeline is a set of data processing elements connected in series. These fetch, decode, execute, store are called data processing elements. Fetch, decode, execute are called data processing elements, where the output of one element is the input of the next one. So pipeline is an speed up technique where multiple instructions are overlapped in execution on a single processor, which is very important. That is executed on a single processor. It is very important to understand that. So when I say it is a single processor, I have a single processor which is a uniprocessor system which performs fetch, decode, execute and store. So multiple instructions are overlapped in execution on a processor. How? Means let us take the same example: fetch, decode, execute and store. First instruction 1 will be in the fetch state and next state it will be here, third stage it is here, and at the fourth stage it is here. When it is in the state at the 1, 2, 3, 4, this is first stage, this is second stage, this is third stage. So here it comes I2 when I have I1 here and I2 here, I3 comes here. So when I2 here, I3 here, I4 comes. So what's happening at fourth stage? Multiple instructions are getting executed and their execution is getting overlapped. This is most important. Its execution is getting overlapped. It is most important thing. Its execution is getting overlapped. So this is most important thing in pipeline processing. The elements of a pipeline are often executed in parallel, or the elements in the pipeline are often executed in parallel or in time sliced fashion. In that case, some amount of buffer storage is often inserted between elements. So they can be executed in parallel. That means fetch is doing when fetch is doing instruction execution, sorry, decode is doing instruction 1, fetch will do instruction 2. So all these things are happening parallel. If they are not parallel, then you need some buffer. You need some buffer to store all the elements. So this is about uh, buffering. Buffer means our data buffer. It is a region of a physical memory storage used to temporarily store the data while it is being moved from one place to another place. That means why it is required to have buffer means fetch, decode, execute and store. The time required for fetch may be, let's assume, 10 nanoseconds, and decode might take 15 nanoseconds. The moment fetch completes, it cannot directly send to decode because decode is still doing decoding for the next one, for the previous one. So in that case you need some buffer. See, buffer is not required when the fetch takes 5 seconds, decode takes 5 seconds, 5 nanoseconds, and execute takes 5 nanoseconds, and store takes 5 nanoseconds. If each stage takes same amount of time, then this is not required. Then buffer is not required. But buffer is required when you have, when this fetch, decode, execute, store takes, so this buffer is required when buffer is required if the fetch takes 5 nanoseconds and decode takes, for example, 10 nanoseconds, or it may take 15 nanoseconds, store may take 20 nanoseconds. So in this case, the fetch completes in 5 nanoseconds, but decode takes 10 nanoseconds. So then in that case you need buffer. So let's take he has taken some example. What is that means? 4 loads of laundry that needed to washed, dried and folded. So the task has been divided into, that is, 3 different tasks, that is folding and so here we have 3 tasks: wash, dry and folded. So wash, dry and folded. Wash, dry and folded. Wash takes 30 minutes, dry takes 40 minutes and fold takes 20 minutes. Now can you guess where buffer is required? Yes, buffer is required here and sometimes here also. So we have one washer, one dryer, and one folding station. What is the most efficient way to get 4 loads of laundry done? We have 4 loads. What is the efficient way means? By this time you can get, when one load L1 is being washed, which takes 30 minutes. Next, after 30 minutes, it moves to drying. It takes 40 minutes. When it's doing 40 minutes, another load can come. It can be washed. It can complete within 30 minutes and ready for drying, but ready is not yet completed, so we need a buffer. And when after 30 minutes or after 40 minutes, what happens? This L1 moves to folded. It takes 20 minutes. When it's doing L1, L2 is sent for washing, and L3 for L2 is sent for dry, L3 is sent for washing. So what is the most efficient way to get 4 loads of laundry means? So this is the real world example that has been given. So here what happening? I have a time frame. These are the 4 loads A, B, C, D. So 30 seconds for washing, 30 minutes for washing, 40 minutes for drying, 20 minutes for folding. See this stage. In general, if there is no pipelining, 70 plus 20, 30 minutes for washing, 40 minutes for drying, 20 minutes for folding. So total 90 minutes is required for one load. So for 4 loads, how much time is required? 90 multiplied by 4, 360 minutes divided by 60, that is 6 hours. If you don't follow pipelining technique, if you just follow sequential process or sequential technique, task takes total 6 hours. The task takes a total of 6 hours. So it takes total of 6 hours. But what happens is that if it is called non-pipeline laundry. If you apply non-pipeline technique, it takes 6 hours. Now let us see what happens if you take the pipeline architecture or pipeline technique, if you follow it. So when load A is getting first washed, then when it completes, when it moves for dry, then second thing will come. Second thing will continue when first one is doing dry. Similarly, third one will continue. By this time, what happens? Using this method, the laundry would be done by 3.5 hours. See here, with the pipeline architecture, the first load will be finished after 3:30 hours. That means after 210 minutes. Then after this, for every 20 minutes, you get one laundry to be completed. This is the most important thing. For every 30 seconds or for 20 minutes, you get one laundry. So this is the most efficient way, efficient technique which can be used for faster processing. This is called pipeline technique. Now we discuss in detail about how this is implemented. Computers like laundry are typically perform the exact same steps for every instruction. That is, I tell you in the beginning that fetch an instruction is the one stage, decoding is another stage, execute is another stage, read memory to get input is another stage, write results. So read and store. So I can divide this instruction cycle into fetch, decode, execute. While executing, you may read this together. We call it as one group, and store. So this is about instruction execution process. Fetch means fetch an instruction from memory. D means decode the instruction. E means execute the instruction, and R means read the memory, and write means write the result back to memory. Now the instruction execution process lends itself naturally to pipeline. See, instruction execution has these steps. These should fit for pipeline. All the processes will not fit for pipeline. So overlap, the instruction execution can be overlapped. It should be overlapped. Then only we can implement this process. Otherwise, it's not possible. So overlap the subtasks of the instructions fetch, decode, and execute. Instruction pipeline has 6 operations. So it's divided into 6 operations. You know, one is fetching the instruction, decode instruction, calculate operands, fetch operands, execute instruction, and write the results. So we know fetch, decode, execute, and store. Two new things had been added, that is calculate operands and fetch operands. This calculate is operand is nothing but what type of addressing mode the instruction contains. Accordingly, fetch it. So these two are related to, these two stages are related to uh, operands, fetching of operands. So before fetching of operands, we should um, uh, identify the type of addressing mode they use. Next we see how the instruction pipeline can be implemented over here. Now let us try to understand the instruction pipeline, that is fetching of instruction. First stage is fetching of an instruction. The fetching of an instruction, how it can be done means, so we try to understand the operations of these 6 stages. The first one is fetching of instruction. The instruction fetch, stage is responsible for obtaining the requested instruction from memory. It has to fetch an instruction from memory, instruction whose address is stored at PC, program counter register. The instruction and the program counter are stored in the register as a temporary register. Remember, instruction is stored in instruction register, and the instruction is fetched from memory, and on what basis? Data stored, the address stored on program counter. So the program counter stores an address of the instruction to be fetched from the memory. Once the fetching is done, it is stored in an instruction register, special register. So it involves two registers. One is program counter and another is instruction register. Next stage is decoding the instruction. Decoding stage is responsible for decoding the instruction and sending out various control lines to other parts of the processor, and this is done by control unit. Next, calculate operand. Calculate operand stage is where any calculations are performed. The main component in this stage is ALU. ALU is made up of arithmetic and logic capabilities. Next, fetch operands and execute instructions. Fetch operands and execute instruction stage are responsible for storing and loading values to and from memory. They are also responsible for input and output from processor respectively. And the next stage is writing the results. WO, writing the results stage, is responsible for writing the result of the calculation, memory access, or input to a register, into a register file. So these are the 6 stages. What are they? They are fetch the instruction, decode instruction, calculate operands, fetch operands, execute instruction, and write the results. So these are the 4 stages: 1, 2, 3, 4, 5, and 6. So these are the different stages of instruction execution pipeline in a typical computer. Now let us see the timing diagram for instruction pipeline. See the uh, these are the time, and this is the one time frame, the amount of time required for completing instruction of 1. So instruction 1 completes its execution, that is fetch, decode, calculate operand, fetch operand, instruction execute, and write results back. So this is the amount of time required for executing one instruction. So what happens, instruction 2 execution starts when the first instruction is getting decoded because of this overlapping. Next, instruction 3. For instruction 3, when the first instruction is calculated, operands is doing, you will perform all this fetching of instruction starts here. And for instruction 4, this starts here. And for instruction 5, comparing with first instruction, when you are executing at the 5th stage of the first instruction, 5th instruction is getting fetched. And finally 6, that is when you are writing results back, the instruction of sixth one will complete. See, uh, first for completing the instruction execution of first instruction, it takes 6 time frames, 6 nanoseconds, but the second instruction execution will complete readily at 7, third one complete at 8, like that. 7, 8, 9, it will complete in 14. So what happening here, if you observe carefully, for if it is not pipeline, if it is non-pipeline, then each instruction takes 6 nanoseconds. So 9 instruction execution takes 9 into 6, that is 54 54 nanoseconds if it is non-pipeline. If it is pipeline, what's happening? For completing 9 instruction in case of pipeline, this is for non-pipeline. In case of pipeline, it is taking 14 nanoseconds. See how much time got reduced, and the average of execution is nothing but not even 2 nanoseconds. 1.5 nanoseconds. So the instruction execution dropped from 6 nanoseconds to 1.5 nanoseconds in case of pipeline. If you use non-pipeline, this is the case. If you use pipeline, this is the case. See how much difference exists. And this average of 1.5 will reduce further with number of instructions. So the advantage is that pipeline makes efficient use of resources, quicker time of execution of large number of, see, if you have large number of instructions, even the average execution time, if you have some 1 million instructions, it is less than 1 nanoseconds. It can even further go to 1 nanoseconds, which is a very advantageous compared to 6 nanoseconds. The parallelism is invisible to the programmer, and the programmer is not aware of this parallelism. This is one kind of parallelism. This is type of parallelism that can be achieved by using a single processor. Which is most important. Can pipelining get us into trouble? The point here is, are there any disadvantages? So far we are discussing about the advantages of pipelining, but are there any advantages? Definitely there is a downfall. We know that pipeline cannot be implemented for every process. If a pipeline has to be implemented, there are certain rules. One is the total process has to be divided into different stages. All stages can be operated simultaneously, and the output of one stage should go as an input for next stage. So there are some conditions. But what is the downside of this pipelining means? There are certain limitations. Hazards means some kind of limitations. Structural hazards. Attempt to use the same resource by two different instructions at same time. See, attempt to use the same resources, then this is a limitation. What is this kind of limitation means? If the instruction 1 and instruction 2. If both want to access same resource, then you cannot achieve pipelining. Because until unless I1 resource completely utilizes is at stage 1, see this is at stage 2 and they are at stage 1, and this, but at stage 1 and stage 2 they both want same resource. What happens? This has to be in wait state. Then it affects the performance. Are you getting what I'm trying to say? Next, data hazards. Attempts to use data before it is ready. This is one kind of bigger issue. Let me explain this. It is very important to understand. Right, stage 1, stage 2, stage 3, stage 4. At stage 4, the instruction 1 updates data D1, but in stage 2, I3 wants to use the same data. It leads to data inconsistency, because in general what happens, when I1 completes the execution, then I2 should complete, then I3 should complete. Then when I3 starts, I1 should get complete. That means it should complete updating this data. Then I3 should use. Simple statement, let me give an example. One is scanf percentile D A and some increment and printf percentile D A. So before doing increment, if you try to print, what happens? It is not good, because the programmer expects user to complete increment the value of a, then print. If these two are pipeline, when it is in the middle of updating, you can't print the value. This is called data hazards. Control hazards. Attempt to make a decision about a program control flow before the condition has been evaluated and the new PC target address is calculated. So these are the three types of hazards: structural, data, and control hazards.